So this is a project I'm very happy about. This is, you'll see the title is a bit provocative, like I'm asking this question, I'll motivate the question and give you kind of a like high-level context on all those terms that appear on the screen. But the reason I'm very happy about this project is when trying to answer this question with my co-authors, we stumbled upon a very nice series of applications of this. And this is a work that in fact started, I think, 5 years ago. We sort of were prompted to answer this type of questions, and at the time we could not crack the problem, and then we let it sit for a few years. And recently, a few months back, we came back at this problem and finally managed to crack it. So what's the context? So first I should tell you about bosonic systems. So bosonic systems, they're ubiquitous. One example is just quantum states of light. These are systems that lead to remarkable physics. So here you have this kind of schematic description of what some of you may know as the Hong-Mandel effect, which is this thing that if I send two photons on a 50-50 beam splitter, the two photons will always sort of bunch together. They always will come out, unlike classical balls or classical particles, they will always come out on the same side. Okay, and so they have kind of this unique, bosonic particles have this kind of unique statistical behavior, which you can actually leverage in quantum computing, for example. So you may have heard of boson sampling. Boson sampling is this kind of simple model that allows you to solve problems with linear optics that you cannot solve with classical computers. And the way this is achieved is by generalizing this, like providing some mathematical generalization of this effect. So my sort of background is mostly on quantum information theory. So I'm always motivated by the applications that relate to quantum technologies. So here is a bit about bosonic systems in this context. So you can find bosonic systems, as I said, in quantum light, but also in modes of superconducting systems. And on the left-hand side here, you see this kind of artistic depiction of what the quantum internet could be. There's ongoing effort to build networks of quantum computers that are connected by photonic links. And so here the bosons, they're useful as information carriers, just like for classical communication in fiber optics. And on the right-hand side, you see a figure that I stole from this paper that says, if you're looking at bosonic modes in superconducting devices, they're essentially useful for many, many different things. Quantum computation, quantum simulation, communication, sensing. And in the rest of the talk, I'll be more interested about the quantum computation aspect. But yeah, it's good to keep in mind that those systems are really worthwhile studying in the context of quantum technology. Okay, and with regards to quantum computing, there was this landmark quantum computational advantage experiment by the group in USTC in 2020, where it demonstrated this variant of boson sampling that is known as Gaussian boson sampling, which, if you don't know what this is, you can think of it as I'm sending a bunch of quantum state of light into a linear interferometer, which is this huge optics table on the right-hand side. Then in the output, I'm measuring the number of particles that I see in every output port. And it turns out that sampling these statistics is very hard for classical computers. So you can think of this as kind of a milestone demonstration of, yes, with quantum physics, we can achieve, in some sense, programmable computations that cannot be achieved with classical computers. And on the more maybe industry side now, there are many different companies and startups that are pushing to build a quantum computer using bosonic systems. So here I put a bunch of examples. For instance, AWS Quantum, Amazon is trying to build quantum computing technologies in the fault-tolerant era with CAD qubits, which essentially are using superconducting bosonic cavities to encode discrete variable quantum information. Okay, so this is all on, let's say, the state of quantum technologies. On the theoretical side, typically we don't necessarily divide our way of thinking in, let's say, fermions and bosons and spins. One way of sort of making this division is between what you can think of as discrete variable and continuous variable. Here in the context of quantum computing. So what are those formalisms? Well, The main difference essentially is the type of Hilbert space that you use. So in quantum mechanics, I have my quantum states that they live in some space, that's a Hilbert space. And in this discrete variable approach, this Hilbert space is finite dimensional. Whereas in the continuous variable space, which is in some sense a bit more general, you can use infinite dimensional Hilbert spaces. Okay? And the reason you do that is because it allows to be a bit more expressive with the type of observables that you can use in this context. So in the discrete variable world, you have operators that act on this finite dimensional Hilbert space. They are bounded. You can think of those as corresponding to degrees of freedom that are discrete, that are finite, like the spin or the polarization of a photon, these kind of degrees of freedom. Whereas in the continuous variable world, you can describe, again, bounded operators, but also unbounded ones, meaning they have kind of infinite spectrum, even continuous spectrum. And this allows you to describe a bit more degrees of freedom, such as position and momentum. So you can think of, I have some particle somewhere, I want to measure the position. In principle, like mathematically, this should give me a result that is a continuous real number, let's say. And so for this, you need infinite dimensional Hilbert spaces to account for these type of degrees of freedom. And if you ask, how can I do quantum computing with this? If my goal is to build a quantum computer, should I think more in the setting of finite dimensional Hilbert spaces, infinite dimensional Hilbert spaces? Is there even any difference between the two? And in this context, the way you perform computation is just like for a classical computer, you're going to chain together a bunch of gates. Okay, so you can think of these as logical gates. And the property that you want from those gates is that they allow you to implement any type of quantum evolution, right? Any type of, let's say, reasonable quantum evolution. So those type of gate sets, we call them universal. So in the discrete variable setting, the way universal gate sets are defined, loosely speaking, is that it's, let's say, a finite set of gates that you can combine together in sequence in such a way that in the end you manage to approximate any target unitary evolution. Okay? In the continuous variable world, the definition is a bit different, and the reason is just because you're looking at this infinite dimensional Hilbert spaces. On that space, you have unitary evolutions that are kind of crazy, like they can generate infinite energy in finite time, or these kind of things. So these, you don't really want to consider them. They're not really physical, like it's not something you can think of implementing in the lab. And so instead, you can make a restriction, and the typical definition, which dates back to 1999, is that like a gate set will be deemed universal if it can approximate any unitary evolution that is generated by a certain family of Hamiltonians. Okay, so what's this family? So here I call them polynomial Hamiltonians. It's any Hamiltonian that you can write as a polynomial function. In the Q and P operators that you see just above, those Q and P operators are the observables for position and momentum. They're sort of the canonical operators for describing bosonic systems. And the name of the relation that you see just above is the canonical commutation relation for bosonic systems. Okay? And here is just to fix ideas. Here's a bunch of examples of universal gate sets. So, I mean, if you're familiar with this, in the discrete variable setting, you can work, let's say, with the Hadamard gate, the CNOT gate, the T gate, and you can combine just these three gates in sequence to approximate any unitary evolution. And in the continuous variable case, the exact nature of those objects doesn't matter too much, but what you can see is it's always some unitary that I generate using a Hamiltonian, which is here in the exponent, and that Hamiltonian is like some polynomial of Q and P, right? So the index here just labels subsystems, and here I have some polynomial of degree 2, some other polynomial of degree 2, one polynomial of degree 3, and somehow you can argue that, okay, if I combine those things, then I can generate any unitary evolution generated by polynomial Hamiltonians, yes?
So, for example, the atom of hydrogen is not one of those kind of Hamiltonians, right?
Yeah, exactly. So that would be the hydrogen atom, like up to some constant. So Q squared plus P squared is the number operator. Yeah.
But I mean, the Hamiltonian of the hydrogen atom also has a 1 over Q in your variable, right? Because of the potential.
Yeah, so it wouldn't be, then it would be part of this class, yeah.
Okay. And isn't that an important example to also be able to approximate?
That's a great question. And so what we're going to see in a second is indeed like, doesn't this seem a bit restrictive, right? Like, okay, I'm sure polynomial Hamiltonians, you could argue they appear in many systems, but not all systems, right? So that's a good question. I'm going to come back to it. Right. Sorry, I thought you meant harmonic oscillator. Yes, and one thing that I want to mention that is a bit technical is something that we have for finite-dimensional systems, but we don't have for infinite-dimensional systems, which is the so-called Solovay-Kittel theorem. And this is something that is foundational to doing quantum computing in finite-dimensional hyperspaces. Essentially what this theorem tells you is that the way you can approximate your unitary evolutions here is very efficient, no matter the gate set you start from. Right? And this is important because if you want to sort of develop a theory of computing and be able to classify what's the complexity of the problems that I can solve with quantum computers, maybe you don't want that you need a different complexity theory for each type of gate that you choose. You want, in some sense, some really universality in the way I can choose the gate set. And so this is ensured in the finite-dimensional case by the Solovay-Kittel theorem, and we don't have something like this in the infinite-dimensional case. Okay? And so, to come back to your question, indeed there's kind of this weird problem here, which I'll refer to as the continuous variable universality problem, where there's a big discrepancy between those two definitions of universality, one in the finite-dimensional setting and one in the infinite-dimensional setting. Because in the finite-dimensional setting, we are ensured that we can approximate any unitary evolution. In the infinite-dimensional one, we are restricting to specific Hamiltonians, and it's not so clear that all unitary evolutions generated by polynomial Hamiltonians allow you to go anywhere in the hyperspace. Like for instance, it could be that I start from a specific state. There are states that I cannot even get close to if I just have an evolution that is governed by polynomial Hamiltonians. Okay, so this is kind of, and this has been left open since the definition of universality in the 1999. Okay. So yeah, maybe one thing that I should say, of course, this is also the way I wrote the slide, but kind of on the left-hand side, everything is green and nice and bounded and finite-dimensional. On the right-hand side, things are red and you have like unbounded operators, infinite-dimensional spaces. And the general consensus is somehow that the formalism on the right-hand side is a bit more tricky to work with, right? And so maybe you'd want like ways of simplifying what happens on the right and ways of describing it maybe in finite-dimensional hyperspaces so that the math is simple, so that we can simulate those systems on classical computers, on quantum computers. And these I'll loosely refer to as effective descriptions. So you want a way to describe what happens in the bosonic setting with some description that is a bit simpler. So what are these effective descriptions? So examples of things that you can do. You can take your state space, which is this infinite-dimensional hyperspace, and you can say, oh, I want to reduce this space. I want to simplify it. And similarly, you can use, let's say, effective dynamics. You might want to say, oh, maybe I don't want any Hamiltonian, I don't want to allow any type of Hamiltonian, but maybe specific Hamiltonians. Okay, so in practice, this would be like the way you would get to an effective state space is you would start from this infinite-dimensional hyperspace and truncate it to some finite-dimensional hyperspace. So you would get some effective dimension depending on the parameters of your system. One way of doing this is if you know, let's say, that the energy of your system doesn't go beyond a certain value, then you can truncate based on that energy bound. And as a remark, this is really a necessary step because if you want to simulate bosonic systems, you just cannot keep track of this infinite-dimensional hyperspace on any reasonable computer. So at some point, you need to truncate and not keep all the parameters in your description. And with regards to dynamics, so if you restrict to specific families of Hamiltonians, well, you could ask which one. So this is, of course, going to depend on the type of physical system at hand. You have effective Hamiltonians, depending on the system that you study. But as I explained, in the quantum computing literature and quantum information theory literature, typically the class of Hamiltonians are those polynomial Hamiltonians, that are polynomial in position and momentum. And as I mentioned, they are used to define CD universality. Okay, and the original question of the talk, can we consider these these effective descriptions as complete, is motivated by essentially what could go wrong. So if you make those assumptions, it's nice because now things are easier to work with. But those are just assumptions that you can restrict to those effective dimensions. So let me give you examples of what could go wrong. So the first thing is that this sort of foundational relation for bosonic systems, which is at the basis of the statistics of bosonic systems, in fact, there is mathematically no way to satisfy such a relation, even approximately, in any finite dimensional hyperspace. And so one way to see this is if you assume that this was true in some finite dimensional Hilbert space, we get two linear operators here. If you take the trace in this expression, the trace of the commutator is going to give you 0 because you'll have trace of AB is trace of BA. But on the right-hand side, you'll get I times the dimension of the space, right? And so there's no finite dimensional Hilbert space where you can actually satisfy this relation. And a bit more technical, you can also show that there's fundamental differences between the set of quantum correlations in the finite and infinite dimensional cases. So you have correlations that you can produce with quantum systems of infinite dimensions that you just cannot obtain with finite dimensional systems. Yeah. And on the side of dynamics, so this was your point, and I think it's a great point. Not all bosonic systems have native polynomial Hamiltonians. So, okay, the example I took was a bit different, but it's like kind of this Josephson junction type of Hamiltonian where you have a cosine of some quadrature operator, so some canonical operator. And in practice, when you do the math, it's not really clear that I can take this object and expand it as a Taylor series and maybe truncate. It depends on the state that the Hamiltonian is acting on. So it's really not so clear that you can just use polynomial Hamiltonians and be fine with it. And then again, just to recap what I said about the CV universality problem, polynomial Hamiltonians, they could generate a very restricted set, as far as we know, of unitary evolution. And so is it a good definition of universality? Should we really call that universality? Okay, and one way to summarize this, again, is can we trust those effective descriptions to actually capture real effects, right? If they're, if the bosonic statistics actually require this kind of mathematical relation to hold, if I go to a finite dimensional Hilbert space and I, see what happens there, am I not missing things that I wouldn't get in the real world? Yeah.
Can I ask a question about what you mean by real effects? So, because for example, I don't know most of these, but like the one I know is at the bottom left. So,
yes.
So this is true, but it's not like you can observe it.
Absolutely.
Still about the mathematics. So is there anything here that is observable? And your questions applies to, because this is it's still only formalism that we decide on.
Yeah, so this is what I mean by real effect, observable in the, and if I give you the answer now, I mean, this is the rest of the talk, but yes, I will give you an answer. But your point is true that here indeed, for this specific point, if I add a bit of noise to those correlations, or I can approximate those correlations up to arbitrary precision using Hilbert spaces of growing.
Yeah, I mean, just even the one there, this commutator is part of the formalism, but it's not something that I can observe. Like I cannot observe this relation, the commutator of
well,
so.
Yeah, you'd have to define properly what you mean by observe. Like there have been experiments that sort of verify the validity of the commutator. Like
okay, so then my question is just, okay, so take such experiment.
Yeah.
You cannot model it using a finite dimensional system?
You can.
Okay.
Yeah. But
this is not the question that you're talking about, or you will.
I will explain why. Yeah. But I want to stress that it is not obvious. Yeah. Okay, so here's the question. Here's the answer. Yes, we can trust those effective descriptions. I'll explain in which sense these effective descriptions capture real effects, like what we mean by that. But I think more importantly than that, like if you're a physicist, you might just think, sure, like I knew it all along. Yeah, I can always truncate the Hilbert space. It's not so surprising, and maybe polynomial Hamiltonians, they seem very expressive, so it's maybe not so surprising, right? I think that is true, and that is the right intuition, but the other thing I want to stress is the fact that you get many things along the way when you try to answer this question formally. And so the two main results that we get are as follows. So one is unitary truncation. And what this result tells you is that if I have any infinite dimensional unitary that is physical, I'll define formally what I mean by physical. Then I can formally truncate it and have a guarantee on the precision of the truncated, the precision of the approximation of the infinite dimensional unitary evolution by the truncated one. Okay, so this is, let's say, with regards to what you can do for effective state space description. Yes, you can truncate for unitary evolutions. And then the other result that we get is this, what I call discrete variable universality of polynomial Hamiltonians. And this is kind of a strong result that says, you give me any linear operator acting on a finite dimensional Hilbert space, I can reproduce it exactly with a polynomial Hamiltonian. So it really formalizes this idea that, yes, with polynomial Hamiltons, you can sort of do everything in a finite dimensional space. And then I'll explain what happens in infinite dimensional space. Okay, so before I go into the details of those two theories, is there any questions? Seems clear. Okay, so unitary truncation. So just I'll recap. I have an infinite dimensional physical unitary evolution, and I want to replace that by something finite dimensional. Okay, so how do you do this? We're going to truncate. So I just give you a bit of notations here. So I'm starting with my Hilbert space that is infinite dimensional. This is some orthonormal basis for the space. In quantum optics, this is known as particle number basis, Fock basis, a photon number basis, and I'll have also a truncated Hilbert space, which is the same space, but I only have particles going all the way to, let's say, big N. Okay, we can, on that orthonormal basis, we can define an operator by its action on the basis. So here, this is this N with a hat. This is the so-called number operator, and it just counts the number of particles that you have in your system. And when I talk about energy, what I'm referring to is the expectation value of that operator, so the average particle number, right? Okay, and now I need to explain what I mean by physical unitary operators. So as I said, if you allow for any unitary operators, you get, unitary evolutions that will increase the energy to infinity in finite time. So this is something that, of course, we cannot achieve in our universe. And so we want to put a limit, and this is the way the limit is put. We want that if I start from a state that has a finite number of particles, I want that the average energy after the evolution, I want it to be finite. Okay, so this is exactly what this equation tells. I start from a state psi that has finite number of particles, I evolve it under U, and then the average energy, you take the supremum over all such states, this should be some finite number. And this I denote as this like EU of n, and this number, you can think of it as, let's say, it's sort of the maximum energy involved when I'm evolving a state that has at most n particles with a unitary evolution U.
Sorry.
Yeah?
Is this important for the theorem that the spectrum of your original continuous Hamiltonian is discrete? Or, so for example, a free particle on a full real line, can it also be described this way? Or
that's a good question.
At least within some time limit, right?
Yes, so intuition says yes, but indeed we're using somewhere in the proof that, like to simplify a few things, we are using the fact that the energy Hamiltonian has discrete spectrum. So I don't know. I would say yes, but...
So in case we should imagine putting the quantum system that we're interested in some box, regularized.
Yeah.
Is this a strictly weaker assumption than the polynomial Hamiltonians generate the unitary assumption?
Yes.
So there exists polynomial Hamiltonians that do not send finite energy to infinite energy.
Well, okay, no, sorry, it's incomparable. So no, polynomial Hamiltonians, they will send you to finite energy, but they will also never send you to states that have infinite, like fourth moment.
Okay.
Here I'm not even, like, this wouldn't feel very physical as well, but I'm not even forbidding this. Like, it could be the case that you start with a state that has a finite fourth moment, and in finite time, it maps you to a state that has infinite fourth moment. I'm just asking that the second moment, meaning here the average energy, stays bounded. But, okay, and the last thing that I should introduce is sort of a formal tool, is we're talking about approximating some infinite dimensional thing with some finite dimensional object. So we need a notion for like how to compare those things. So this is a bit technical, but typically in finite dimensional Hilbert space, what you use is the so-called diamond norm to compare channels. Okay, here we are going only to compare unitary channels. If you try to use that in infinite dimensions, things just fail because this is kind of like the way I can put it is you can always distinguish two channels by using states that have infinite energy, essentially. That's sort of the idea. So you want to use a topology that is a bit more strict. And the way you do it is this definition. So if you know what the diamond norm is, then it's the same definition, but you add this energy bound. If you don't know what it is, I can just give you like kind of this high-level explanation. So this energy constraint diamond norm is telling you what is like my best distinguishing strategy between two channels if I'm using a state that has some energy bound. Okay. Another thing that I should say, this is again kind of a mathematical technicality, but an important one. Whenever you're working in infinite dimensional spaces, the different topologies that you can use, the different norms, they're no longer equivalent. So like the type of result you can get will really depend on the choice of topology. So somehow, this is why I'm spending a bit of time like saying why this is in some sense physically motivated, this choice, because you might get different choices by using different topologies. Okay, so with all these notations introduced, I can restate the theorem and try to make it a tiny bit more formal. So the theorem is over there. And what this statement is saying here is if you pick the cutoff high enough, then essentially things are going to be good. And so what is high enough? So you have some energy parameter, you have some precision parameter, this is this epsilon over there, and you have a target unitary, which is this infinite dimensional U, that has the property that it doesn't map states of finite energy to states of infinite energy. So this EU quantity here is some finite number. And the theorem tells you if you cut off at D, that scales like this in terms of the relevant parameters, then you have a guarantee that you can take your infinite dimensional object and replace it by some finite dimensional object of size, in fact, D plus 1, because we start at 0, but essentially of size D. And now in the theorem, there's this kind of weird notation where I'm not comparing U with the finite dimensional object, I'm comparing U with the finite dimensional object plus something else. So again, this is just a mathematical technicality. So this object is an operator that lives in an infinite dimensional space. So to actually compare it with this finite dimensional object, I need to append, some like block diagonal structure object here that could be anything. So the theorem tells you that there exists a cutoff operator such that whatever you append, you have the closeness between the finite dimensional object and the infinite dimensional object. Okay, and in sort of matrix form, if you think of this as your infinite dimensional basis, this is the truncated subspace where VD is, and then you have something, but you don't care what it is, on the rest of the space. Okay, so how is this achieved? Well, of course, the intuition is pretty simple. We want to truncate. So I start with this infinite dimensional object, and I'm going to truncate it to some finite dimensional space. The problem is when you do that, if you start from a unitary operator and you truncate, the object that you get is no longer unitary. So there's this kind of second step of rounding your truncation to something that is unitary. And okay, many technical details, but at the end of the day, you get this theorem. And now, what does this theorem tell you? So at the conceptual level, it tells you, yes, you're good, you can always truncate. At the practical level, maybe I should not say practical, but at the application level, this tells you that if you care about simulating bosonic dynamics, like some unitary evolution of a bosonic system, then you can do that on some finite size quantum computer, as long as the number of parameters that you track is high enough. And this theorem gives you a guarantee of like what is like this number of parameters that you should keep track of. Okay, so this is for the unitary truncation. And for the universality of the polynomial Hamiltonians, so the first part was on how do you describe effectively your states and unitary evolutions in state space. And now this is going to be about dynamics. Why can we sort of safely say that we can work with polynomial Hamiltonians? And the first brick of reasoning will be this one, that if you have any finite dimensional unitary, I can generate that with polynomial Hamiltonians. Okay, so this is, with the same notations, this is how the theorem looks. So compared to before we were starting with this infinite dimensional unitary and trying to truncate it to a finite dimensional object. Now it's the other way around. I have a finite dimensional unitary, and I'm trying to reproduce it, to generate it with some infinite dimensional operator, which is this polynomial Hamiltonian. So this is how it looks like. In fact, here I'm working with just a Hermitian operator in some finite dimensional space, but this could be any linear operator, in fact. And what this result tells you is given this linear operator on your finite dimensional space, you can always build a polynomial. So this is just a notation for a polynomial, such that this polynomial in Q and P, in your position momentum mechanical observable, will be essentially A on the finite dimensional subspace, and something else on the rest of the space. Again, this time it's reversed, but again, I'm comparing some finite dimensional object with some infinite dimensional object, so I sort of need to append something so that the objects are comparable. So this is, in Fock basis, how this would look like. I'm reproducing exactly the operator that I started from on the finite dimensional space, and there's something happening on the rest of the space. And because of this block diagonal structure, if you think of A as being some Hamiltonian, when I exponentiate this Hamiltonian to get the unitary evolution, you still get this block diagonal structure. And so in particular, on the subspace that you're interested in, the unitary evolution generated by the polynomial Hamiltonian will be the same as the unitary evolution generated by the operator that you're starting from. So it really tells you, like, there's a recipe for you give me any finite dimensional operator, I give you a polynomial Hamiltonian that does exactly the same thing on some subspace. Okay, the way this works is also constructive. So there's a sort of simple algorithm that starts from the description of this operator and gives you back the polynomial. And okay, without entering too much into the details, this has to do with just interpolating the right values, essentially. Yes?
How do you decide which states you keep from the infinite ones? Like, how do you decide which ones are the relevant ones?
So here, everything sort of is a consequence of this average energy bound. So you know that you have a state that has a bounded energy, and when you have something that has a bounded energy, you can show that you can sort of truncate it to a good precision. And the states that that remain are the first states in the basis, in this infinite basis that I call the Fock basis. Now, here is a sort of, those theorems, they're valid for this choice of, like, this way of looking at what energy means. But if you have a truncation with respect to another Hamiltonian, then it would be like the eigenbasis for that Hamiltonian. So kind of the low energy eigenbasis of that Hamiltonian. Okay, and so the last thing that I want to say is what happens when you combine those two results. Like, so far we've not fully answered the CV universality problem. I told you we can go from any state to any other state, but I didn't tell you how to approximate any infinite dimensional unitary evolution that is physical using those polynomial Hamiltonians. For now, this is a universality in a finite dimensional space. Okay, and if you just sort of read the two statements in a row and you check that the math checks out, in fact, this tells you that this exact universality of polynomial Hamiltonians in finite dimensional system translates to an approximate universality in the infinite dimensional setting. So what you get is that any infinite dimensional physical unitary evolution, you can rigorously approximate it to any precision by a sequence of unitary gates generated by polynomial Hamiltonians. So essentially this definition of universality is sound. And so it resolves the CV universality problem. And the last question that you want to answer now is, okay, what about the Solovay-Kitaev theorem? So now we know that you give me any unitary, I can approximate it using sequences of unitary evolutions generated by polynomial Hamiltonians. Can I do that efficiently? Okay, and this is kind of a very hard question because you're dealing with infinite dimensional operators and you're trying to compile a certain sequence of gates in such a way that you generate your target unitary. And the answer is yes, you can do that in sort of a restricted way. I mean, I'm happy to discuss after the talk like the details, but yes, you can get this Solovay-Kitaev in the infinite dimensional setting. Meaning, compared to the universality theorem, it's exactly the same thing, but now you ask that the sequence is a short sequence, that you don't need many gates. And also there's an algorithm for finding the sequence of gates. And the high level intuition is that you are just going to use the unitary truncation result to sort of approximate what you're trying to do on some very high dimensional hyperspace. on that finite dimensional Hilbert space, you will use the Solovay-Kitaev for finite dimensional systems. Then this will give you a short sequence of gates, which you can think of as qubit gates, if you wish, that is short and that approximates your finite dimensional unitary evolution. Now, each gate in that sequence is finite dimensional. I can use the fact that I can realize any finite dimensional unitary using polynomial Hamiltonian, that's this result. And the result is this short sequence of now infinite dimensional unitary gates that are generated by polynomial Hamiltonians. And then there's a bit of work to show that like at each step you can track like the error that you make in such a way that the result that you get at the end is this one. Okay, and at a high level, the way this is done essentially is for each effective dimension that you choose, you can pick your favorite qubit universal gate set for that dimension. You can realize it with polynomial Hamiltonians. And the collection of all those polynomial Hamiltonians together, they generate universal sets of gates for infinite dimensional unitaries, which allow you to give short sequences essentially. Okay, so let me conclude. So we started by looking at these systems of bosons. And what we showed is we can truncate the unitary evolutions for such bosonic systems. And this allows us to try to simulate those systems using discrete variable systems like qubit computers, essentially. And then on the other way, we said, okay, anything that is finite dimensional, I can also realize with a simulator where I can sort of tune my polynomial Hamiltonians. And I have universal quantum control, which means I can go anywhere in the Hilbert space using polynomial Hamiltonians. And finally, when you combine those two results, you get universal effective gate sets that do satisfy the Solovay-Kitaev theorem. Okay, so I'll just flash a few open questions and I'll conclude here. Thank you.